Nitrous acid is a versatile reagent in organic chemistry, but because it is unstable, we must prepare it freshly in the reaction flask using sodium nitrite and hydrochloric acid at low temperatures. Today, we explore how it distinguishes different types of amines. The reaction outcome depends heavily on the degree of substitution on the nitrogen atom. Primary and tertiary amines follow completely different chemical paths, resulting in visible differences that chemists use for identification in the laboratory. The active species in these reactions is the nitrosyl cation, NO+. This electron-poor electrophile attacks the lone pair of electrons on the nitrogen of the amine, initiating a series of complex molecular transformations. When a primary aliphatic amine reacts with nitrous acid at 0 to 5 degrees Celsius, it forms an extremely unstable aliphatic diazonium salt. These salts are so reactive that they decompose almost immediately at room temperature. As the diazonium salt decomposes, it releases nitrogen gas, which appears as brisk effervescence in the test tube. This leaves behind a highly reactive carbocation, which then reacts with water or other nucleophiles in the solution. The resulting carbocation typically reacts with water to form an alcohol as the major product. However, depending on the structure, you might also see the formation of alkenes or alkyl halides as secondary products of the reaction. Unlike aliphatic amines, primary aromatic amines like aniline form relatively stable diazonium salts at low temperatures. The positive charge is delocalized into the benzene ring through resonance, preventing immediate decomposition into nitrogen gas. Tertiary aliphatic amines behave differently. Because they lack a hydrogen atom on the nitrogen to undergo diazotization, they simply undergo an acid-base reaction to form a clear, water-soluble nitrite salt. No visible gas is produced. In tertiary aromatic amines, the nitrogen is blocked. Instead, the nitrosyl cation attacks the electron-rich benzene ring, specifically at the para position, leading to a unique substitution reaction rather than a nitrogen-centered reaction. The result is a green-colored nitroso compound. This distinct color change is a diagnostic test for tertiary aromatic amines, contrasting sharply with the colorless solutions or gas evolution seen in other amine types. Let's look at ethylamine. As a primary aliphatic amine, it reacts with nitrous acid to produce ethanol and nitrogen gas. If you performed this in a lab, you would see immediate bubbling as the gas escapes. In contrast, trimethylamine, a tertiary aliphatic amine, simply dissolves further into the acidic medium to form trimethylammonium nitrite. The solution remains clear and no gas is evolved, making it easy to distinguish from ethylamine. The stability of aromatic diazonium salts allows them to be used as intermediates. By treating the stable salt with various reagents, such as cuprous chloride, we can synthesize a wide variety of substituted aromatic compounds like chlorobenzene. The mechanism for primary amines involves several steps: initial nitrosation of the nitrogen, followed by a proton shift and the loss of a water molecule to generate the characteristic triple-bonded diazonium cation. Tertiary amines form an unstable N-nitrosoammonium ion. Because there is no hydrogen on the nitrogen to be removed, the reaction cannot proceed toward a diazonium salt, leading back to the salt equilibrium or ring substitution. To summarize, primary aliphatic amines give nitrogen gas and alcohols. Primary aromatics give stable diazonium salts. Tertiary aliphatics form soluble salts without gas, while tertiary aromatics yield green paranitroso compounds. Test your knowledge: which of these would produce a bright green product when reacted with nitrous acid? The correct answer is C, N-dimethylaniline, due to the electrophilic aromatic substitution at the para position. Understanding these reactions is essential for identifying unknown amines and for synthetic organic chemistry. By observing gas evolution or color changes, we can determine the exact nature of the amine. Generated by Vision Solve AI.